Hi guys, Frankenstein here. Today I want us to look at the full wave center tip. Um, Sometimes it's called a biphase, so you must know the name. So it's either a full wave center tip or either a biphase. So any of the names are still corrected for us, still marked correctly. So what we need to know is how does a full wave center tip, or like I like calling it a biphase. How does a biphase look like? So a biphase is basically accounting for both cycles, but it looks weird from the from the bridge rectifier itself. So how does the center tip look like? Let's draw it. So I have something like that. Okay, then I have a bigger tap. Okay, we're gonna have some bit of some coils there. You go there. And then what you must know is that there's a weird line there in the middle, just in the middle. I'm sure that's the middle, right? I'm sure that is the middle. So you've got a resistor there, right? And then what you must know is that you've got a diode here, very important. And you've got another diode there. Same biasing. Remember, for the positive cycle, in respect to the positive cycle, this will be a positive, this will be a negative section. So in the respect of the positive cycle, let's listen to me, I'm saying in respect to the positive cycle. But if during the positive cycle, this one will be on, this one will be off, right? And then during for the negative cycle, where the thing is, the nodes will be interchanged. This will be negative, this one will be positive. So this one will be on and that one will be off. And this one will be on. And then, but they are using the same resistor. Take that into account that they are using the same resistor. So surely this one will be the negative, this one will be the positive. So surely our load is taken from there. That's our load. Are we still fine? Okay. Now let's try to remove these off positions, so if we were to like draw, the input wave will be looking something like that. And then the output will be something like that. Same thing. So it's the same thing as the bridge rectifier, but this one is like another configuration. But there's downfalls itself. There's downfalls. So let's try and solve for everything in the circuit, which usually we look for E1 peak. We look for E2 peak. We look for Vmax. We look for Vf. And we later on found out that Vmax is actually equal to VDC. And we're looking for IDC. And looking for PIV. Very important. You must know that we're looking for those. Okay. So let's go through it. Let's go through it and just make a tick box of itself there. So that will be E1 peak. Yeah, that it is. Yeah, let me just leave it there. That's fine. So let's say, for example, we are given this is the following. We are given the resistance there to be the same one. Let's say we have 420 ohms, And the diode there, I said if you're not told anything, it's a silicon. So you're not told anything here, it's a silicon diode. Silicon diode. And then we're told that since we know that this is the primary side, this is the secondary side, right? So what we are told is that the voltage which is given, actually let's give the turns ratio. The turns ratio is 10:1, and we know that that is N1, can label it as N1, and that is N. So that is 1, so that can be labeled as N2. This is N1, right? And what we are given is that actually we're given that we're given 220 volts. And I said if we're not told if this 220 volts is a peak or RMS value, we just assume it's a RMS voltage. So that's VRMS. Ne? Now they want us to solve for the following. So let's try and solve for this equation. Not for the equation, for the following actually. So first of all, we need to take E peak and find out what E peak is. So E peak so I use this one, my regular one. Okay, so E1 peak is equal to, remember, it's equal to ERMS, or VRMS or ERMS, still the same thing. VRMS multiplied by √2, remember. Now let's fill in that. So what is our VRMS? VRMS is 220 multiplied by √2. How much are we getting? Let's check. So 220 multiplied by square root 2. So it's gonna be 311.13 volts. Yeah? Now it's right on. Remember I told you that when you deal with pulsar plasma most of the time, you would need those answers prerequisitely. So you must make sure you don't lose them. Make sure you keep them with you. It's very important. Very important. So let's remove that. Okay, fine. Now since we've covered this guy, let's find E2. So remember I said that we need to, for us to find E2, we must know this formula that N, shouldn't start with that one, that E1 peak divided by E2 peak is equal to what? N1 divided by N2, right? You must always know that this one here must correlate with this one here, and those two must correlate with this two there. So meaning we can substitute that E2 is actually 311.13 is equal to 10/1 divided by E2 peak. Now for us to find E2 peak, we're going to say E2 peak is equal to 311.13 divided by 10. What did I do here? I cross multiplied. So let's see how much did we get. So divided by 10, we're getting 31.113 volts, right? That is our E2 peak. Let's put it safe, nice and safe. So that's number 1 there. So 1, 2. Let's erase the left. What's left? Let's erase it. Don't need it anymore. Okay. So we've solved for E2. Let's see Vmax. What is Vmax? Remember I said Vmax is nothing else but the voltage E2 peak subtracting the volt drop, but Vmax is equal to E2 peak. But remember I said you are subtracting the number of diodes which are on for one cycle only, not for both cycles, but only for one cycle. How many diodes are on for one cycle? For the positive, let's relate to positive cycle. When this one is on, this one is off. When this one is off, this one is on, remember. So meaning that we are using one diode per cycle. So should we tell minus 1 time VD? So I don't have to write 1 time, I can just write VD because it's just one VD. I'm saying this because remember that VD was 2 times VD in the previous question, right? But now it's 1 VD. But now there's a thing which you must account for, that we can't actually minus E2 peak, because remember that we are having one resistor, right? And we are having 2 diodes, and this one is only clipping the thingy, clipping the positive cycle, and this one is clipping the negative. Sorry, it's clipping, this one is clipping the negative cycle, and this one is clipping the positive cycle, right? So I have to match them. So basically it's acting as 2 independent circuits. So I must say that I'm going to split my E2 peak to this first one and split my E2 peak for the second one. So Shiguti, I have 2 circuits, which is circuit 1 and circuit 2. So I must split since I have the same resistor, so Shiguti, the voltage divider will work in a way. So Shiguti, I will split my volts, so I must divide there by 2. Because I'm having 2 more like separate equations, because this one is going to clip the negative cycle, this one will clip the positive cycle. So, and then after they're going to mesh them together as just one perfect circuit, right? So that's what you must understand as well. So let's go through it. So this is going to be equal to 31.113 minus VD 0.7 divided by 2 there. So let's punch it and see. Our Vmax is 14.86 volts. So that's Vmax. So let's keep our Vmax very safe. Vmax. No, 3. Now since we've found our Vmax, let's go and find VDC or V average. So VDC or V average, I told you must relate to the graphs. So if you have those graphs, and this is the input graph, which will be looking like this, and the output will be looking like something like this, right? So what you must know is that right there it's also pi, and right there it's also pi there, yabo. But now what is there? That is Vmax, right? That is Vmax. Agreed? That is Vmax. Agreed? Yes. So what you will do is the same thing, you don't change anything. So it's gonna be VDC is actually equal to, or V average, actually let me keep it there. Let me continue with this line. So it's gonna be equal to 2 times VDC, because you're adding these two, cycle 1 and cycle 2, right? Divided by pi. Nothing fancy, guys. And then we continue. So it's gonna be 2 times Vmax is what? It's 14.18 divided by pi. Then we check. So our VDC is actually 9.03 volts. So I want to keep it safe. So let me just make some room there for it. Remove this. Still fine, you can remove it. Then even here, I can remove this gibberish. Okay. there for VDC. PIV there, still fine. Okay, so there's our voltage there. 4. So what you must remember is that we've found V average. Now we are looking for IDC, and I said V is actually VAR, so it's gonna be VR, IR, and then to find current it's gonna be IDC, and you must use VDC as well, and divided by what? By R load, because I said VDC, it is the voltage across this resistor. That is the voltage we are trying to carry out, right? So let's make sure we understand that. And this is going to be our load. So because this is the load, right? So we're going to have 9.03 divided by the load, which is 420 ohms. So let's see how much are we getting there. So it's going to be 21.5 milliamps. So that is our current which is flowing there. Now let's find what is, actually let me just keep this, it's fine. So VAR, get out bro. So that is IDC, which happens to be number 5. Now what is PIV here? Because in the previous question we said PIV is equal to E2 max, right? Sorry, we said PIV is equal to what? V max. I'm like E2 max, that's crazy. So in the previous video we said PIV is equal to E2 max, right? But now we can't say PIV is equal to E2, so it's equal to E2 max. We can't say that because we've got a bit of a problem in a way, yabo? So what we need to do is actually relate to the maximum voltage V max, yabo? So relating to it, we need to understand that PIV is nothing else but 2 times V max. Nothing exaggerated. You just have to just know that PIV is equal to 2 times V max. So 2 times what? 14.86. So that happens to be 29.72. And that is our answer there, guys. It's calm. So yeah, guys, I think that's all the analysis we need. But for the graphs, the AC graphs, the input and output graphs, we'll do a separate video on that. Just keep a lookout onto it and make sure that you click that subscribe button and also the notification button so that you're notified next time I upload another video concerning electrical engineering, guys. Cheers, guys.